Hi, my name is Chris Kinsley. I'm a professor at the University of Guelph Alfred campus and a researcher with the Ontario Rural Wastewater Centre. What we'll be describing here today is a hybrid constructed wetland system to treat domestic wastewater. We call it a hybrid system because it consists of two components, a horizontal flow subsurface wetland followed by a vertical flow subsurface wetland. So the reason we're using a hybrid wetland system here is because we're interested in not only removing organic matter and solids, which is what wetlands typically will remove very effectively, but also we're looking at nutrients in this system. So we want to remove both nitrogen and phosphorus. So in order to remove nitrogen, we have to do two things. First, we have to convert the ammonia, which is the primary form of nitrogen in wastewater, into nitrate. So that's the nitrification reaction, which takes a lot of oxygen. So we're converting NH3 into NO3. So there's 3 oxygen molecules we have to add for each molecule of ammonia. And that's where the vertical wetland comes into play, because it's vertical flow, so the water is trickling through an unsaturated media, so lots of oxygen from the air can enter into the filter, and the nitrifying bacteria can easily take that oxygen to make the transformation. So what we've done here is we have domestic wastewater first going into a 2-compartment septic tank to remove some of the solids, and then it flows into a header pipe in the subsurface flow horizontal wetland here, and then the wastewater will flow horizontally through the saturated bed where most of the organic matter and solids will be removed. After the horizontal bed, the wastewater flows through a phosphorus slag filter, so that's a byproduct from the steel industry, which is good at removing phosphorus through precipitation of calcium phosphate. After the slag filter, we move into the vertical flow wetland, where, as I said, the ammonia in the wastewater is converted into nitrates. And from there, we recycle the wastewater back into the header line of subsurface flow wetland, where the nitrified wastewater comes into contact with the anoxic bacteria in the subsurface flow wetland. There's not a lot of oxygen transfer through the gravel here, and fresh carbon coming out of the fresh wastewater. So those two conditions are necessary for denitrifying bacteria to convert nitrate, NO3, into N2 gas and return nitrogen into the atmosphere. So with this loop, we can very effectively remove total nitrogen in the system. Here we're at the tail end of the subsurface flow wetland. So this is where we installed our blast furnace slag filter. So what this is just a waste product from the steel industry. So there's a lot of calcium oxide in this waste product, and it's very inexpensive because the steel industry has to basically get rid of this waste. And the calcium reacts with phosphate, which is the primary form of phosphorus in wastewater, creates calcium phosphate, so it precipitates on the surface. Now the disadvantage of this is because we're leaching out so much calcium, it also bumps the pH up to very high values, which is very good for the precipitation of phosphorus, but creates another problem in terms of the wastewater treatment. So we found with this filter material is it worked very effectively for the first 18 months of treatment. So we had below 1 milligram per liter of effluent phosphorus from the cell for the first 18 months. And we saw was initially the pH was very high, above 12, and then it started dropping down. Then once it reached 9.5, 10, we saw the phosphorus concentration starting to creep up. So this tells us that there's a finite lifespan to the use of this particular slag material, and we need to do some more work to determine a product that would last, say, longer than 2 years as a phosphorus filtering material. We're here at the vertical flow wetland. So this was constructed in 3 layers. The top layer is 20 centimeters of peat. So the reason for this was to equilibrate the pH that was very high coming out of the slag filter. The peat is acidic, so that lowered the pH down to around pH of 8. So that worked very effectively as a balancing media. Below the peat we have 40 centimeters of a coarse filter sand. So that is the treatment zone where the nitrifying bacteria are going to develop. And then the bottom 20 centimeters is gravel, just as a filtration layer to bring the wastewater out of the filter. So this is the vertical filter. And then from here we pump back to the header line to recycle the effluent in order to complete the denitrification cycle. So this has been very effective at not only transforming all of the ammonia into nitrate, but also has been very effective at polishing any BOD or organic matter that escapes the horizontal flow filter. So in this experiment we looked at two variables. Number one, we looked at season, so the difference in operating between summertime in Canada and wintertime in Canada. Summertime our average temperatures were about 20 degrees plus or minus 2, and in wintertime the temperatures were 4 degrees plus or minus 2. So those are significant difference in temperature. What we found was there was slightly better treatment in the summertime. However, combining the horizontal and the vertical filter together, we maintained tertiary quality effluent, meaning BOD is less than 10 milligrams per liter in both seasons. And this brings us to the second experiment, which was increasing the flow rate. So our design flow rate for this system was 2.8 meters cubed of wastewater per day. We tried that flow rate, we doubled it to 5.6, and we tripled it to 8.4 meters cubed per day. And in each of those three flow regimes, we were able to, with the combination of both the horizontal and the vertical, maintain tertiary quality effluent, so less than 10 milligrams per liter of BOD coming out the effluent. So we're very pleased here. We're very pleased with the quality of the water. So if we can just focus in on the water here. So as you can see, the effluent is very clear. There's almost no solids in the water. And as I said, we've been able to convert any ammonia present to nitrate, and the BOD is pretty much non-detect during the summertime and less than 10 during the wintertime.